Chapter 11, Section 6 is on surfaces in space. So far in this chapter, we've looked at two surfaces, one being the sphere and the other being a plane in space. This section is going to look at more surfaces. The objectives are to recognize and write equations of cylindrical surfaces and recognize and write equations of quadric surfaces. This slide shows three examples of cylindrical surfaces. Now the first one does look like a cylinder and the other two don't, but they're still classified as cylindrical surfaces. And a way to recognize these are by looking at the equations. The right circular cylinder pictured here on the top left is the equation x squared plus y squared is equal to a squared, where a can be any constant. Now that you would typically think of as a circle in 2 dimensions. Well, when we start to examine these in space, notice that the missing variable is z. So z could be anything as long as x squared plus y squared is equal to a squared. So we say that the cylinder is created by the circle cross section and allowing z to be anything. So it's really an infinite cylindrical tube that's parallel to the z-axis. The z is the missing variable. Now, in the top right portion of the screen here, we have another cylindrical surface, which is a sine curve. The equation is z equals sine x, and you would typically think of this as a sine curve. And notice the equation is missing a y. So in space, y could be anything as long as z is equal to sine x. So we see the red trace here is the xy trace, and then the y could be anything. So we have this cylindrical surface which appears to be a wave, infinite wave, where y could be anything to the right and left. On the bottom center of the screen, we have another cylindrical surface where the equation is z equals y squared. Notice that it's missing the x variable. So the x can be anything in space as long as the z equals y squared. Now z equals y squared is that parabola. The red trace is the xy trace, yz trace. And then the parallel line to the x-axis, that means that x can be anything. So we have this surface, a U-shaped surface that is parallel to the x-axis. Now, quadric surfaces are in the following form. The equation of a quadric surface in space is a second degree equation. That means the highest exponent is 2 in 3 variables. The general form is ax squared plus by squared plus cz squared plus dxy plus exy plus fyz plus gx plus hy plus iz plus j. That's a whole lot to say. That equals 0. That's their general form. Now there are 6 basic types of quadric surfaces, and they are the ellipsoid, hyperboloid of 1 sheet, hyperboloid of 2 sheet, elliptic cone, elliptic paraboloid, and the hyperbolic paraboloid. We're going to get a chance to see all of these types of surfaces in the following slides. On this slide, the top, we have the ellipsoid. Now the ellipsoids are going to be in the form of x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. And the way you would generate the graph of this by hand is by sketching traces. And we have the 3 traces shown here, the red frame around the ellipsoid. It kind of looks like a football shape. And the thing to notice with those is that all the x, y, z's are squared, they're positive, and when you add them up, it does equal 1. Now, very similar to the equation, we have the hyperboloid of 1 sheet, but the graph is very different. There are similarities. In this case, the x squared and the y squared are both positive, but there's a minus z squared term in there. So what that does is it creates hyperbolas as the traces. So again, we'll be looking at what it means to draw these traces in a few slides, but that's how you can recognize a hyperboloid of 1 sheet. This has the minus z squared term, so notice that the hyperboloid of 1 sheet is opening up around the z-axis, and also that it's equal to 1. If this were, if the y squared term had a minus in front of it, but the z squared term had a plus in front of it, then it would be opening up around the y-axis. So depending on the coefficient of the x squared, y squared, z squared, if there's one that's negative and the sum equals 1, then it's going to be opening up around that axis. This slide shows the hyperboloid of two sheets, very similar to the one we just did, but notice there are two negative coefficients for the x squared and the y squared. In this case, the z squared is positive. It's opening up around the z, but notice that the hyperboloid ends up separating, forming two sheets or two surfaces, rather than in the previous example, it was one surface. So we call that two sheets there. And the way, again, you can recognize if the squared terms will equal 1 and there's two negative coefficients, that's going to be a hyperboloid of two sheets. The bottom one is the elliptic cone, and it looks like it's actually two cones point to point. And the way you can recognize elliptic cone is by looking at the squared terms. They're going to equal 0. Now we have two positive coefficients and a minus, which leads to this graph of the elliptic cone. This slide shows the elliptic paraboloid on the top. Now in this case, the equation is in the form of z equals x squared over a squared plus y squared over b squared. Notice the z term is not squared. So we have an x squared term and a y squared term added together equals z. We end up with this paraboloid shape, elliptic paraboloid, kind of like a bowl. And the way you can recognize paraboloids is that, again, one of the terms does not have a square and the other terms added together, both positive coefficients. So we have these traces end up being parabolas, which form the elliptic paraboloid. On the bottom, we have the hyperbolic paraboloid. In this example, the z is not squared. It's equal to the y squared over b squared minus x squared over a squared. Now that forms this shape right here. It's called a hyperbolic paraboloid. Now you can also think of this as a saddle, or at least the point right there is called a saddle point, where if you look at it from one angle, you have a parabola that opens up, and then you look at it from another angle, it's a parabola that opens down. So that coefficients there, in this case the y squared has a positive coefficient, so it's a parabola that opens up in the yz trace, and the negative in front of the x squared term shows a parabola that opens down in the xz trace. So we have this hyperbolic paraboloid. We can also refer to this as a saddle shape, kind of like a Pringle. Here's an example of classifying and sketching the surface given by 4x squared minus 3y squared plus 12z squared plus 12 equals 0. Now you can pause and try to do this one on your own. And when you're done making your sketch, come back and view the slide to see the solution. Now notice there are squared terms here. X is squared, y is squared, and z is squared. And also notice that the 4 has a positive coefficient. The x squared has a positive coefficient, the y is negative, and the z is positive. So think about those examples and see which one would apply where we have two positive squared terms and a negative squared term. So you do have to do some rearranging using algebra to make it look like one of the surface forms on the previous slides. So one way to do that is to take this equation that's in standard form and to rearrange the terms. Now what's been done here is if you divide everything by the greatest common factor of the coefficients, if we divide everything by 12, in this case divide by negative 12, we get the following equation. And what we're going to end up doing is to add 1 to both sides so that we get the squared terms equal to 1. Now this is standard form. Notice the y is positive, y squared term is positive, coefficient where the x and z squared terms have a negative coefficient. So this is going to be a hyperboloid. And because both of those square terms are negative, we can say it's a hyperboloid of two sheets. Now the y squared term has a positive coefficient, so we could say it's opening up around, the hyperboloid is opening up around the y-axis. To sketch the graph of this surface, it does help to find the traces in the coordinate planes. To find the xy trace, you're going to set the z in the original equation equal to 0 and simplify. When you simplify that, you get y squared over 4 minus x squared over 3 equals 1. That is a hyperbola, and you may have to go back to your pre-calc classes to refresh yourselves on how to sketch parabolas. All right, so the xy trace is found by setting y equal to 0 in the original equation and simplifying to get this equation. X squared over 3 plus z squared over 1 equals negative 1. Now that has no trace because it's impossible for two squared terms with positive coefficients to add up to a negative number. So on the xy plane, the graph is not going to have a trace. And the yz trace is found by setting x equal to 0. And this equation results, when you plug in 0 and simplify the equation, you get y squared over 4 minus z squared over 1 equals 1. This is our hyperbola shape because you have the squared terms equal to 1. One is a positive coefficient, one is a negative coefficient. Now you put those three traces together. What I like to do is draw those three separate graphs and then rearrange them, form them, combine them so that we get a graph in 3 dimensions. So we have, well, actually the two traces, the YZ trace and the XY trace. You'll see the two hyperbolas that form together form that hyperboloid of two sheets. In the next set of videos, I'll actually go through examples and write out and show you the steps of finding these or sketching these surfaces.